Okay, what's up everybody? Welcome back. Today we're talking a little bit more about diagonalizability. So, if you recall, this was just all about when you can take an operator on a finite dimensional vector space and find a basis for that vector space such that the matrix of that operator with respect to that basis is diagonal. Our first result for today, just picking up where we left off last time, is all about the minimal polynomial of a diagonalizable operator. So, quick recap. In part one, we defined diagonalizable operators. We defined eigenspaces. Remember, the eigenspace E lambda t was just the null space of t minus lambda I. So we defined this for all scalars lambda. And we did this so that we didn't have to talk about whether or not lambda was an eigenvalue. It just turns out that the eigenspace is non-trivial precisely when lambda is an eigenvalue. All right. So we showed that if you have distinct eigenvalues, then the sum of the eigenspaces corresponding to those distinct eigenvalues is a direct sum. Cool. We went on then and we proved a pretty long theorem here, which gave a bunch of conditions that were equivalent to diagonalizability. The first one was that the vector space that T is an operator on has a basis consisting only of eigenvectors of the operator. The next one is that the vector space is the direct sum of the eigenspaces corresponding to the distinct eigenvalues of that operator. And then finally, just the dimension of V is equal to the sum of the dimension of the eigenspaces, which is a pretty immediate consequence of the previous part of this right here, since the dimension is additive over a direct sum. All right, sweet. We ended with a quick example. So let's get back and start talking about more consequences of diagonalizability, or more characterizations of it. So our first one is as follows. We'll suppose V is finite dimensional, and we'll let T be an operator on V. Then our claim is that T is diagonalizable if and only if. So I'm going to super underline that because this is a full characterization. It's equivalent. The minimal polynomial of T is equal to z minus lambda 1, product all the way down through z minus lambda m, for some list of distinct numbers lambda 1 through lambda m in the field. All right, this actually has a very nice parallel to something that we saw much earlier. So, if you remember, so here, let me pull this up real quick. All right, here we go. So, this was way back when we talked about upper triangularity, which I guess was just one section ago, not too long ago. But we proved that if T was an operator on V, and V has a basis with respect to which T has an upper triangular matrix, then the minimal polynomial of T is a scalar multiple of the product of T minus lambda 1I through Z minus lambda 1 through Z minus lambda n, for lambda 1 through lambda n, the diagonal entries of that matrix, which we also later showed were, in fact, the eigenvalues of T. So, combining these two things together, these two facts, and returning back to diagonalizability, here's the difference. Notice, upper triangular matrices are a more general type of matrix than diagonal ones. That is, diagonal matrices are certainly all upper triangular, but upper triangular matrices cannot be diagonalized or not be diagonal. So the real difference between diagonalizability and upper triangularizability is whether or not you have repeated factors in your minimal polynomial. That is, here we've got z minus lambda 1 all the way through z minus lambda m for distinct lambda 1 through lambda m. If I have the minimal polynomial with potentially some repeats, that is like lambda, 2 is equal to lambda 4 or something like that, right? Then I don't have diagonalizability. I only have upper triangularizability. So in a certain sense, diagonalizability is all about the minimal polynomial being square free. That is, not divisible by z minus lambda for some lambda. It's z minus lambda squared. That's what I'm saying. So there's no factors of it that are squares. Kind of cool. All right. Well, let's prove this. Proof. The proof is this is a relatively substantial proof. So let's go through it. So first, suppose T is diagonalizable. Okay, then, really quick, returning back to what we proved last time, if T is diagonalizable, then V has a basis consisting of eigenvectors of T. We proved that. So let's say that. Okay, so let's suppose T is diagonalizable. Let me get this to a proper level of zoom. Then V has a basis of eigenvectors of T. Okay. Let V1 through Vn be such a basis. And let lambda 1 through lambda, notice now m, be the distinct eigenvalues of T. So here, m and n may not be the same. It may be the case that you have more eigenvectors here in this basis than you have distinct eigenvalues. That is, a couple of them could belong to the same eigenspace. Okay, now think about this. So then, for each vk, there exists lambda j such that T minus lambda ji vk is equal to 0, i.e. each of these eigenvectors has to belong to some eigenspace, which is the null space of T minus one of the lambda something for one of the lambdas that is an eigenvalue of T. Okay, so think about this. T minus lambda 1i product all the way down through T minus lambda mi is equal to the 0 operator, since it is 0 on a basis. And this just follows from the fact that P of T, Q of T equals Q of T, P of T for polys P and Q. That is, polynomials of an operator commute with each other. So you can flip the order of any of these terms there and zero out this entire basis of eigenvectors. Oh, sweet. Okay. Hence, the minimal polynomial of T is a polynomial multiple of z minus lambda 1 through ... z minus lambda m. That is, if you plug in T to this polynomial, it zeroes it out. So, whatever it is, it's got to be a polynomial multiple of the minimal polynomial. Oh, okay, cool. Now, in fact, it is exactly the minimal polynomial. Why? Think about this. Since any divisor of it leaves some eigenspace out of its null space. That is, if I pull any one of these z minus lambdas out of here, then there's going to be some eigenvector, or in fact potentially multiple ones belonging to the same eigenspace, that I don't zero out. So to have all of the eigenspaces in its null space, which is the same as having all of V in its null space, since, as we proved last time, V is the direct sum of the eigenspaces corresponding to the distinct eigenvalues of T, this is actually its minimal polynomial. Okay. Now, in the other direction, suppose the minimal polynomial of t is z minus lambda 1 all the way down through product z minus lambda m for some list of distinct lambda 1 through lambda m in the field. Okay, so in this case, let me give you an idea of how we're going to do this. We will do induction on M. Okay, so when we do induction on M, the base case is going to be easy. And then the inductive step, what we're going to do is we're going to break down V into a piece that is smaller dimensional than V and has a basis of eigenvectors. And then we're going to make sure that the other piece, the leftover piece, only has eigenvectors. So I'll talk through that in just a moment after we do the base case. But this is the meaty part of this proof. It is perhaps a little bit confusing on your first pass through it, but I'll try to break it down into a nice and digestible way, or nice and digestible format. So first off, base case. Let m equal 1. Then t minus lambda 1I is equal to 0. That is, if the minimal polynomial is just z minus lambda 1, then plug in t, it zeroes it out. You'll get t minus lambda 1I equals 0, and t is equal to lambda 1I. So t is a scalar multiple of the identity, and the matrix of t is diagonal with respect to any basis of V. If you don't believe that, convince yourself of this. I'll say, by recalling the definition of the matrix of T. And here I will very briefly erase that little period right there. Okay, and that finishes off the inductive step. Okay, cool. So, if you don't believe that, just go back, remind yourself of the definition of the matrix of T, just write it down, and see what having this would mean for you. I promise you, if you actually do it, you'll go, oh, okay, that is as easy as you said. So if you don't see it, just try it out. It's a good exercise. Okay, let's do the inductive step. Suppose our desired result is true for all values less than some m, which we'll say is greater than 1. Okay, since we showed the case of m as 1, we know that it's true for all values less than 1, or for all values less than or equal to 1. So we'll take m to be something bigger than that. All right, here's the idea. Now, what we'll do is, well, here, let me write it out more specifically. And let the minimal polynomial of t be z minus lambda 1 through ... z minus lambda m for some list of distinct lambda 1 through lambda m in the field. Okay, so same thing we're still assuming, but I'll just rewrite it just to make it super clear. Okay, now to do this, what we'll do is we'll break things down into two pieces. We will show that the range of t minus lambda mi has a basis of eigenvectors of t, and that v is equal to range of t minus lambda mi direct sum with the null space of t minus lambda mi. Showing then that any extension of this basis of eigenvectors for range t minus lambda mi adds only more eigenvectors of t, and hence that v has a basis of eigenvectors of t and is therefore diagonalizable. Since, as we showed before, having a basis of eigenvectors is the same as diagonalizability. Okay, so we'll say, let's look at the range of t minus lambda mi. I know that seems kind of unmotivated at this point, but basically what we'll do is we'll try to cut this minimal polynomial down a little bit since we're doing induction on m, the number of terms in the minimal polynomial, if you factor it out. Okay, so we'll show that this piece has a basis of eigenvectors. Then we'll show that v is a direct sum of this piece and the null space of t minus lambda mi, which notice is an eigenspace corresponding to lambda m. All right, now this means that if I take a basis for the range of t minus lambda mi and I extend it to a basis of v, that I'm only adding stuff from the null space of t minus lambda mi right over here. Okay, everything in the null space of t minus lambda mi is in the eigenspace of t corresponding to lambda m. That is, it's an eigenvector. Well, except for the zero vector, I guess. Every non-zero vector in this null space is an eigenvector of t with corresponding eigenvalue lambda m. So this says that if I extend this basis of eigenvectors to a basis of v, it remains a basis of eigenvectors because everything I added was necessarily a non-zero vector belonging to an eigenspace of t. Oh, sweet. All right. So let's keep it going and let's show this. We'll need a second page here. All right. Now, proof continued. Okay. Now to do this is a little bit technical, I guess. It's not too terrible. Okay. First, note that, and then this part is maybe a little bit of a recall, the range of t minus lambda mi is an invariant subspace of t, since range p of t is invariant for any poly, or is invariant, I should say invariant under t for any polynomial p. Okay, so t restricted to the range of t minus lambda mi is in, and I'll write it this way, it's an operator, brutal, bad L, weird script L, on the range of t minus lambda mi. Here, once again, I am slightly abusing notation to use this restriction to mean not just the restriction of the domain, but also the corresponding restriction of the codomain of t. So just since it sends it to itself, we'll write t restricted to range t minus lambda mi to mean the operator that sends range t minus lambda mi to itself in the exact same way that t does. Okay. All right. Now, if u is in the range of t minus lambda m I, then there exists some v in v such that t minus lambda m I, v is equal to u. So, watch this. This is the good part. T minus lambda 1 I, product all the way down through t minus lambda m minus 1 I, u, well, this is equal to t minus lambda 1 I, product all the way down through t minus lambda m minus 1 I, t minus lambda m I, v. But wait a second, this is the minimal polynomial of t, evaluated at t. That's just 0. Hence, whoa, pretty cool, z minus lambda 1, product all the way down through z minus lambda m minus 1, is a polynomial multiple of the minimal polynomial of t restricted to the range of t minus lambda m I. Oh, wait a second. So here's the whole gist of it. This says, hey, plug in any u living in the range of t minus lambda m I to this operator, you get out 0. So since only plugging in u's from the range of t minus lambda m I to this guy with t in there is the same as plugging in anything for this with t restricted to the range of t minus lambda m I in there, then this says that this polynomial zeroes out t restricted to the range of t minus lambda m I. So this is a polynomial operator, hence the polynomial has to be a polynomial multiple of the minimal polynomial of t minus, or t restricted to the range of t minus lambda m I. Oh, what a mouthful. All right, now, by our inductive hypothesis, this means that t restricted to the range of t minus lambda m I is diagonalizable, and hence range t minus lambda m I has a basis of eigenvectors of t restricted to range t minus lambda m I, and therefore also of t. So that is, range of t minus lambda m I has a basis of eigenvalues of t, or of eigenvectors, sorry. A basis of eigenvectors of t. That's what we wanted. Now to show that v is the direct sum of t minus lambda m I's range and its null space, let's let u be in range t minus lambda m I intersect null t minus lambda m I. We show u is equal to 0 to get range t minus lambda m I. Oh, I'm so tired of writing this. Intersect null t minus lambda m I is the 0 set, and get v is equal to the direct sum of the two. Okay, so since u is in the range of t minus lambda mi, well, actually, let me start with slightly backwards here. Let me say this. Since u is in the null space of t minus lambda mi, this will be easier if I present it this way. Since u is in the null space of t minus lambda mi, then tu is equal to lambda mu. Agree with that? Hopefully so. This just says that t minus lambda miu is 0, so just subtract over lambda miu to the other side, and you just get this statement. Okay. By our argument before, zero is equal to t minus lambda 1i, product all the way down through t minus lambda m minus 1 I u, right? Since we can just take right here and then pop it over to have some v there and add on this t minus lambda mi piece there. Okay. But now, watch what this says. Well, just distribute it on through. Do each piece. This says lambda m minus lambda 1, product all the way down through lambda m minus lambda m minus 1 u is equal to 0. Since lambda m minus lambda k is not equal to 0 for k not equal to m, as lambda 1 through lambda m are distinct, this means u is equal to 0. So, we are done. That is, we've got that v is the direct sum of the range of t minus lambda mi and the null space of t minus lambda mi. We showed that the range of t minus lambda mi, this piece right here, has a basis of eigenvectors of t. Everything that lives in the null space here of t minus lambda mi is an eigenvector of t, except for the 0 vector, which is never an eigenvector. Okay, so take a basis for the range of t minus lambda mi. We've got one that's all eigenvectors. Sweet. Extend it to a basis of v. Anything we added came from the null space of t minus lambda mi, which only consists of eigenvectors. That is, everything we added is a non-zero vector since it's part of a basis. So we only added eigenvectors. Hence, we've got a basis for v that's all eigenvectors. This is just the part of the argument here that we spelled out. Okay. So here's where I said it, right down here. We'll show that the range of t minus lambda mi has a basis of eigenvectors of t. We did that. We showed that v is the direct sum of these two. Okay. And this shows that any extension of the basis of range minus t minus lambda mi of eigenvectors contains only more eigenvectors, and thus that v has a basis of eigenvectors. And as we know from part 1, this means that t is diagonalizable. So, we did it. We're done. What a proof. Okay, let's move on to the next part and talk about Gershgorin disks and some consequences. So, if T is diagonalizable and U is a subspace of V that is invariant under T, then T restricted to U is a diagonalizable operator on U. This is a nice and easy consequence that maybe is not actually immediately apparent without the previous result. But now that we've got it, we have a very, very straightforward proof. So, if T is diagonalizable, then the min poly of T is of the form z minus lambda 1 through dot 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 z minus lambda m for some list of distinct lambda 1 through lambda m in the field. We just showed that. So T restricted to U has a minimal polynomial of this form as well, since its minimal polynomial divides the min polynomial of T. Hence, it is also diagonalizable. Boom! Whoa! Basically, all we did was use the last result. We say, hey, if T is diagonalizable, then it's got a minimal polynomial of the form we just proved. That is z minus lambda 1, product all the way down through z minus lambda m for some distinct lambda 1 through lambda m. Now, since this zeroes out T, it certainly zeroes out T restricted to some invariant subspace. All right, that means that this is a polynomial multiple of T restricted to that invariant subspace's minimal polynomial. Hence, its minimal polynomial must also be of this form, just with a few of these factors potentially missing. Whoa. That means that T restricted to the invariant subspace U is also diagonalizable because its minimal polynomial is of the right form. Super cool. All right. Let's take a break from this piece and move on to something that is related, but not quite as closely related. And I will try to motivate this with a nice little picture, kind of. So here's the idea of it. Now, if you don't have a diagonal matrix, you might look at your operator and say, hey, I can't say too much. I don't know too much about what its eigenvalues are and all that stuff, right? If I can't upper triangularize it, at least I don't even know that the eigenvalues are the things in the diagonals of a matrix of it, you know? Here's a nice fact. Basically, think of this. If you take your matrix of an operator with respect to any old basis, well, if that matrix turns out to be diagonal or upper triangular, then the eigenvalues are just on the diagonal. Okay, cool. In particular, if it is upper triangular, then all the eigenvalues are on the diagonal, and that's that. All right. Now, if you don't get a diagonal matrix, how far away from the diagonal entries can the eigenvalues be? The answer is not too far. So this is the idea of the Gershgorin circle theorem, or Gershgorin's disk theorem. So the idea is that we take T, an operator on V, and V1 through Vn, any old basis of V. We'll let A denote the matrix of T with respect to this basis, and we'll say that a Gershgorin disk of T with respect to this basis is just a set of all Z's in the field. Here, F is going to be equal to C, or the reals. It's all of the Z's in the field that are a distance from a diagonal entry, at most the sum of the non-diagonal terms in that same row. So that is the sum from k equals 1 to n of a jk with k not equal to j. So those guys. All right. So here, I'll try to draw kind of like a picture. So let me write it like this. I'll do this as if we're in C here. I'm getting some lag here. I don't know why. Weird. Maybe my pen's almost out of batteries. Whoa. What is going on? Sorry about that, guys. All right, so here we're living in C. All right, my matrix is maybe something that looks like this. I've got like A11, A1, or let me just write it out. How about A11? Let me make sure that's right. A12, A13, A21, A22, A23, A31, A32, A33. This is my matrix A. Okay, maybe I've got A11 over here, A22 over here, and A33 down here. Then here's the whole idea of it. There is a nice little disk around A11, a nice little disk around A3, and potentially some maybe some other disk around A22. These could all get big, who knows? Such that we have the following. The radius right here of this guy is let me write this in. Sorry, let me make this a little bit clearer. This radius right here is A12 plus A13 in absolute value. This radius right here is A31 plus A32. And this radius right here is something like A21 plus A23. Oh, let me make sure that's super clear. There we go. Okay. And all the eigenvalues live in the green part. Or on the boundary, but in these disks. That's what I'm trying to say. Okay, cool. So this is the claim we're going to make. Suppose T is in LV, that is, it's an operator on V, and V1 through Vn is a basis of V. Then each eigenvalue of T is contained in some Gershgorin disk of T with respect to the basis V1 through Vn. That is, it's this picture right here. It says, hey, look, here's your matrix. Put dots at all the diagonal entries, form circles with radius the sum of the absolute values of the non-diagonal parts of each row. All of the eigenvalues live in this. So in the case where your matrix is diagonal, then all of these circles have radius 0, and the eigenvalues are just the things, are just the dots, right? In the case that they're not, in the case of the matrix is not diagonal, it says that the eigenvalues can't be too far away, where too far means further than the sum of the absolute values of the terms in that same row, except for the diagonal term. All right, kind of cool. Let's see if we can prove this. It's actually not a bad proof at all, and it's kind of a nice way to wrap up this section and see why we might care. So let's think about it really quick. How can we get there? Well, let's just start with any old eigenvalue. Let lambda in the field be an eigenvalue of T. Let W in V be a corresponding eigenvector. Terrible C. Okay. Now, since V1 through Vn is a basis of V, there exists C1 through Cn in the field such that W is equal to C1 V1 plus all the way down through Cn Vn. It's a linear combination of the basis elements. Okay. Now apply T to both sides. And just for convenience, writing A for the matrix of T with respect to the basis V1 through Vn. Okay, let's write it out. And I'll do this kind of in a silly way. Okay, so we get, getting a little lag there yet again, lambda W, Well, this is just going to be equal to, here, I'll write it this way. I'll even just say C1 TV1 plus dot 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 all the way down through CN TVN. But I know how to write each one of these, and now I'll put it into summation notation. So I've got my sum with k equals 1 up to n of ck. So I'm just going to write this in summation notation now. And then tvk, well, we know how to write that. This is just going to be a sum with j equals to 1 up to m of a jk v j. So all I have to do is bring that c on inside. I have a sum from k equals 1 to n of the sum from j equals 1 to n, since I can always distribute multiplication across a sum, of ck ajk vj. And since it doesn't matter what order I sum things up, and I can switch these two sums around, and I get a sum from j equals 1 to n, and a sum from k equals 1 to n of ck ajk, and now I can pull it out of vj. Agree with this? And I maybe have made my 1 there look kind of unclear. That's a 1 still sitting over here. Okay. Now, I've just figured out what the coefficients are over here. Okay. So, the sum of ck, lagging out. I don't know what is going on with this thing. ck ajk, so this sum here is from k equals 1 to n, is equal to lambda cj, just from over here, right? Okay. All we have to do is one kind of silly step now. Okay, let's write it out. So, here's what I'll do. I will write it this way. So now that I've got this equation, hence, I will take the diagonal term over here and subtract it to the other side. Lambda cj minus, and I'll write it out over there, lambda cj minus a jj cj is equal to the sum from k equals 1 to n with k not equal to j of ck ajk. All right, and now I'm going to do it in a fun way. So if I take cj and I pull it out and I divide it over, I get lambda minus ajj is equal to the sum from k equals 1, k not equal to j, up to n of ck over cj, right? A jk. Okay, very cool. Very straightforward. We've got this pretty much set up now. All we have to do, and I'm kind of running out of room here, so I may have to write a little bit on the side right there, is now throw absolute values on both sides. And if I throw absolute values on this side, notice I can carry it through the sum at the cost of an inequality. So the difference here is less than or equal to this sum. And now I can take this absolute value and split it up right there. There's nothing wrong with that. And even more, I can take the absolute value on this fraction and split it up. And here I'll kind of put this little squiggly mark right here. So if Cj in absolute value is the max of C1 dot 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 all the way down through Cn, Ck over Cj is going to be less than or equal to 1, and we're done. Wow, really shoved that in the corner right there. But hey, this works for any old Cj. In particular, just pick the biggest one in absolute value in modulus, and then you can just get rid of this term. You can say less than or equal to, put a 1 right there, and you get ajk, just the sum of the absolute values right there, which is what we wanted to show, since that's the right-hand side of the definition of a Gershgorin disk right there. We've already got the left-hand side, basically, except with an eigenvalue plugged in for z, which is what we wanted to say. We wanted to say the z's were in the Gershgorin disk. They were values that satisfy this inequality. Huh. Okay, cool. I mean, this is a little bit of an aside, so if that proof was kind of pithy, don't worry. It's not, I'm not gonna grill you on it or quiz you on it too much there. But I just thought this is a nice result to kind of tie a bow on our discussion of diagonalizability and just finish off this section with a cool kind of practical result. This one is really great if you want to, for example, check if a matrix is invertible. So for instance, if you can show that 0 doesn't lie in any of the Gershgorin disks, then certainly 0 can't be an eigenvalue, right? So sometimes this is a really easy way to show that something's invertible. It's also a really great thing to use if you're doing numerical calculations, because if you've got, say, some sort of like a floating point system, then there are only ever going to be finitely many points in any one of these Gershgorin disks. And if the Gershgorin disks aren't too big, it might be faster just to check the points in your floating point system that lie inside the Gershgorin disks than to actually go through and compute some approximation of your eigenvalues. It's really neat. All right, I'll see you next time. Have a good one.